Thank you, Dwayne, for the intro. And glad to be here, and nice to see there are still people in the room on a nice Friday afternoon where we would all be touring around Austin if we could help it. In any event, I will talk about Amira, the first machine learning enabled reading assistant. So Amira will listen to students read out loud. These are kindergarten to third grade students, and determine their reading level as well as coaching them so that they can read out loud, saving teachers time and effort listening to each kid individually. So reading is a critical skill in modern society. If a child cannot read fluently by third grade, he is 4 times more likely to drop out of school, and 60% less likely to get a job, and earns 1/3 less income over time. But unfortunately, millions of kids suffer from a severe reading gap. 2/3 of them, that equates to millions of kids, and that's in the US alone. So this is why we are building Amira, which is a smart reading tutor that is based on research in known research in early literacy about how kids actually learn how to read. So Amira can help teachers in 3 main ways. She can administer oral reading fluency tests and save them lots of time listening to each student reading visually, and provide one-on-one real-time interactive tutoring for each student, as well as generate reports so that they can talk to their principals and their school districts about how well their kids are doing. And this report aspect is something that teachers really appreciate. They can take a look at overall picture of how their class are doing based on a national benchmark. And if they want to know how well a particular student is doing, it can chart progress, and it can also highlight the strengths and weaknesses of the student so that it helps the teacher develop lesson plans. And this is a running record view for a student's reading passage. And this shows each word that the student gets correctly and the words that the student pronounced incorrectly in red. So this report is automatically generated, which is nice because what teachers have to do right now is they would sit with a student in the corner with a piece of paper and a pen and literally check off each single word as the student reads along. And imagine having to do that for 30 students in the class. It gets really tedious. So when we talk to teachers, they really liked this particular aspect of the software. And for the one-on-one tutoring mode, Amira contains about 10 different reading interventions. And this is based on early learning psychology that's shown it really helps the kids learn to pronounce each word. And the simplest case, for example, is actually just to repeat the words aloud. And another intervention would be to focus on certain phonemes in particular, like the A in vapid. And yet another method would be to actually clap out the syllables, like caterpillar. And of course, rhyming, as you might imagine, is a good way to help kids learn words as well. So how do we make sure the kids are actually understanding what they're reading? Periodically, if, say, a child seems to be distracted or not paying attention, we're going to ask them these short multiple choice questions. This is to just checking to make sure they're still following along. And this is shown to improve the reading comprehension of the students as well. And now we can take a look under the hood to see how Amira actually works. So the overall pipeline looks as follows, right? Imagine a student is going to sit in front of a computer, like a Chromebook, and the student is going to be wearing a headset with a microphone and speaking into the microphone. And this audio stream is going to pass through AWS, specifically a series of Lambda functions. And that's going to slice the speech stream into individual phrases. And each phrase is going to be scattered into parallel downstream processes. So they get processed by speech recognition modules. And each of these speech recognizers is going to convert the audio into actual words with different confidence scores for each word. And this information gets passed to a machine learning classifier that will tell us whether or not this word is pronounced correctly or not. So a natural question at this point is, why can't we just not use the speech recognizer? And why do we build another classifier on top of it? And that's because kids' accent and way of their speaking is very hard for speech recognizers in general, because they are just not trained on kids' speech, as you might know. So what we empirically found is the raw speech output from the recognizers is anywhere from 30% to 70% right, depending on how well the kid read. And sometimes we've seen when a child is having a bad day, having a cold, stuffy nose, and they mumble and they whisper. So speech recognizers by default do not do well on kids. And that's why we're building a classifier which contain some features. For example, the word-based features take into account of how old the kid is expected to know each word, known as the age of acquisition. And these psychometric measures, like concrete and abstract words, for example, a concrete word is like table or chair or computer, so you can easily picture in your head, versus an abstract word, right, like imagination or belief, and it's harder for kids to understand, and so we don't expect them to learn this vocabulary as early. And word length and syllables, not surprisingly, kids tend to have trouble with longer words and more syllables. Another class of feature is audio-based features. For example, how loud the words are being spoken in each phrase or versus a passage, how slow or fast the words are being spoken, and also their phonemic characteristics like vowels versus consonants. So empirically, a lot of these features ended up being the scaled and normalized versions of the two categories above. So there are a lot of different ways to mispronounce a word. And yeah, kids find all kinds of creative ways to get a word wrong. But there are a bunch of common ways that they mispronounce. So I listed some of them here. For example, they could just drop the last syllable. That's common, we have observed. They could switch around the verb endings, which is a hard concept for a lot of them. Or just scramble the letters, as we see in dyslexics. And a lot of vowel and consonant substitutions we have observed as well. So some of the more interesting mispronunciations are more like word substitutions. So in this case, they could substitute a word that looks visually similar, like rubbed versus rumbled, or similar in meaning, like catch versus get. And so the reason why we're generating these mispronunciations ahead of time is so that the system can know what to listen for, and so they expect these common mistakes that the kids will make. And this word2vec, I will go into a little more detail about, and you've probably heard a nice talk earlier in the day, which went into how word2vec work. Basically, it's a way to capture the similarity between two words, and if we let them be discrete states and calculate that transitional probability between the two words, then we can, for example, find the similar and related words in that manner. So an example is shown here, right? If we want to find the related words to catch, right? So these are some of the top words that relate to catch. And that yellow highlight indicates an actual word substitution that we've seen a kid make when they're reading out loud. So this word2vec method is nice. It works for different parts of speech. Verbs, quasi-verbs, and nouns as well. So I ended up doing something that is not already pre-built. Initially, I looked into the related words API, which if you give it a word, it gives you a list of related words or synonyms. But as we can see here, the list that they have for ears is not the kind of vocabulary that we expect an average 6-year-old to know. So I ended up looking online for children's literature. So I collected kids' books online and fed it into the word2vec neural network so that we can actually generate the related words that are age appropriate. And a fundamental principle of building a classifier is actually this hierarchical concept. For example, if we separate the readers into different groups by certain attributes, like estimated vocabulary size versus reading speed, and this is an example of how we can divide them into 4 groups and create an error detection classifier for each group individually. And this would improve the classifier performance. I found it got better by about 20% in precision and recall. So now I will talk about a really important problem in this use case, which is imbalanced classes. And as you might know, it's when the data is mostly in only one class, right? Very little data in the other class or classes. And it's also relevant for applications like fraud detection, where you have very, very few instances of fraud, or a rare disease, where you're trying to catch a disease that happens 0.005% of the time. And this is a tricky problem, because it's natural, right, to just assume everything is the majority class. So if a student reads really well and makes mistakes less than 5% of the time, then we could say, oh, okay, she got 95% accuracy. But that's not what we're looking for, because we're interested in that minority class, the instances of actual reading errors. So one way to correct this issue is to undersample the majority class, right, and then make the two classes equal. This works really well if we have a lot of data. But as you might imagine, working with children, their speech data is very difficult to collect, because we have to go through the IRB approval process to just even get into the classroom. We talk to the principals, the superintendents, the teachers, just to make sure that they're all on board, right? So we are suffering from a lack of data problem. And so what I'm doing right now is to oversample the minority class. And one way to do this is to synthetically generate data that is similar, right, to the minority class. So the way this works is K means K nearest neighbors. Right here, for example, we pick the 3 nearest neighbors of a particular data point and interpolate between them. So this method, I found, improved the classifier performance again by about 10 to 20%. So now there's a lot of next steps. And in the near future, what we plan to do is to include more feature engineering so that we account for different variety of accents in kids. And we have tested this product so far in some California schools and some New York schools. And we're going to test it in, for example, Tennessee is going to have more of a southern accent if we look at the 3rd graders, for example. That's about the age when they start to develop an accent. And that's when we have to think about how do we account for these accents. We have to cluster them into different groups. Again, all these different ways that we could play with the data. And in the medium term, we are planning to make the tutoring use case more robust. Because right now, it's actually a lot of it is rule-based. We try to decide when is it best to intervene when the kids are making reading mistakes. So we plan to build a more sophisticated deep neural net or a reinforcement learning model, right? So that as we get more data, we can more accurately help each individual kid, right, based on their learning rate, their individual strengths and weaknesses, so that we help each child reach their best outcome. And in the longer term, which is probably maybe a year from now, we could look into an interesting direction, like the satisfaction metrics. So how happy are the students and the teachers with the product? And right now, we don't know exactly for sure. We only have anecdotal evidence, like, oh yeah, some teachers love it, some students love it, some students think that the avatar looks a bit creepy. Like, we've heard all kinds of interesting feedback, and we are going to incorporate all of them in our next cycle of product design. So in my 8 months working at a 12-person company now, I've learned a few lessons over time. So what we found was that if you just add more software engineers to a project, it won't necessarily make it faster, even though we like to think that it would make it faster. So what ended up happening was we had very poor communication because the team is all spread out. So even the core team is spread out across different parts of the US. And you add part-time contractors who are in different parts of the world, and it just became a nightmare to coordinate them. So we just ended up doing it ourselves. And of course, the Git part is the version control aspect of it, which is really for consistency. A lot of previous talks at the conference really hammered it home, like, okay, automate as early as possible, make sure things are reproducible. And this is particular to myself because I am a recovering academic. I have worked a lot in the developing environment, and I'm very excited about making the best feature for the model and then get a rude awakening when it's useless in production because I did not learn beforehand how the data actually gets passed along in the pipeline. So that's a hard lesson for me. And this is another big one, the human label training set. So this took a lot of time. We basically had transcribers. So we hired a few transcribers, give them fast food wages, and they listened to the recordings of the kids, and they decide, oh, okay, this is what I heard, and they wrote down what they heard. But a lot of them actually make mistakes, so then we have to go back and QA what they typed and see, like, is this correct? Is this not correct? And in the beginning, we found like they were making a lot of mistakes, and so we had to iterate on the process and make sure that they're as accurate as possible. Because, right, as we know, supervised learning really depends on this human-labeled training set, right? So yeah, that took a while, and we found out kids break things. They just find all kinds of ways to mess up your flow. We found out don't have a mute button on the headset because they will mute themselves, and then we get no data. They play with the mic, so sometimes they sound far away, sometimes they sound very garbled. And we had one particular student who, the way that he read was very characteristic. Like he would somewhat stutter, but not make the same kind of sound all the time. And it crashed our system. It was our audio just died. And so we have to fix the garbage collection in the pipeline after this case. Yeah, and I really have to thank my collaborators. These are three of the folks I work really closely with. So Mahesh is based in Nashville, like myself. I recruited him just out of a data science camp, and he's out of grad school like myself as well. And we both love Python. He uses PyCharm. I use Spider. I'm just kind of old school that way. Yeah, we also use the Jupyter Notebook, and we trade code snippets a lot. So he today just changed his Slack avatar to the Tutor, and I know he really loves it. Kudos. I highly approve. And Billy is the statistician on the team. And he makes these Bitmojis. And this is his least controversial one. I was not sure whether I wanted to show the other one, but I figured this one is nice and friendly. And Ali is the speech science expert of the team. So he's just very chill, very calm, and we all really need that because right now we're at a really critical time of the company, and the CEO is all nervous, the CTO is all nervous. He's very chill, so I need to learn to be more like him. And I haven't found out a lot about him, but I will most definitely find out about him. Because Billy is based in Kansas, so I only see his face on video Zoom, and Ali is based in the Bay Area, so I don't see him a lot either, other than video. So yeah, and this is a summary of what I was talking about with Amira being able to help teachers in administering reading tests and provide one-on-one tutoring for children. The system encapsulates a lot of speech recognition, natural language processing, and just good old machine learning problems. And we are still chugging away at it. So if a year from now you look us up and we're still around, that means we've succeeded. Thank you.